Okay. Ladies and gentlemen, good afternoon. My name is Ennaoui Ahmed. I am the executive director of this virtual learning university. And with me, Ustad Salem, he is in charge of the all, what is about the platform, and I want to thank him very much for giving us this opportunity. Professor Benyoussef, he will come afterward. He traveled to Fez because one of our colleagues, he passed away, and he's there to support the family, but he will come today, maybe during my talk, hopefully. So I don't know why Mansouri Zouhir, he is not showing up, although he is already inside the platform. But I will start with the introduction. His talk is the fifth talk for PhD research seminar series at Virtual Learning University. Today is Friday, the 7th of April, 2023. I am talking about from Germany, and they will first give an introduction, and hopefully after my introduction, Mr. Mansouri is already there to give his talk. Otherwise, we will see how to make things running. So today, as I did every Friday before the main talk, I want to give introduction on some issue which are related to the talk and related also to the research behind the talk. And today I want to talk about layered materials or 2D materials. Some people call it 2D material. I did some work in the past, and here in the bottom of my slide, you see two papers, and I can send you these two papers if you like. But let's talk about this 2D material, what I have done, and what is very important to know. So we worked when I was in before I get retired from Helmut Center Berlin. I prepared these 2D materials by myself, and as you see here, these materials have a hexagonal structure and with semiconducting properties. And you see here that there is a sandwich where you have the metal, for example, tungsten or molybdenum. Sorry for that, or molybdenum, and sandwiched between two X. It can be sulfur, it can be selenium, it can be tellure, as you see here in this structure here. One of the problems when you are as an experimentalist, one of the problems when you want to prepare this material in the lab, what's happened, you have a substrate. Normally we use sapphire as a substrate. You can also use glass substrate. You can use any substrate. But I use sapphire Al2O3 because it's very stable and support the high temperature. And you see here, this 2D material can be deposited in type 1 or type 2. Type 1 means that the van der Waals surface, which is, for example, sulfur or selenium or tellure atoms, are parallel to the substrate, deposited directly on the substrate. But you can also have the type 2. This means your crystallite will come to be deposited in this configuration type 2, what I call type 2. And they are completely different in terms of electrochemistry and photoelectrochemistry, and they will explain to you this. One of the interesting issue in this 2D material that you can prepare as a monodispersed in a solution, for example, and you can use a kind of solvent, and inside the solvent you can have some ion like lithium, for example, to exfoliate this 2D material, and you can split it into layers, very thin layers. If you are lucky, you can have one layer, but mostly we can have many layers. That's very important to know. And I think the group of Professor Benyoussef and the team working now at the Faculty of Science, Rabat, they are working on this for exploration, not for this 2D material what I'm talking about here, but about phosphine and phosphorine, etc. What I show you here in this picture is a band diagram where you see this 2D material like tungsten disulfide, what I used before, in contact with electrolyte. And one of the problems, if you prepare type 2, this means you have the van der Waals plane perpendicular to the substrate. Then you have a big chance to have some metal which touch the interface. You have some dangling bound here. And therefore, you will have some surface state, what I call SS, surface state. And when you prepare a solar cell, electrochemical solar cell, and you have some dangling bond with this metal, the metal can be tungsten or molybdenum, then you have a lot of surface state. And then there is competition when you illuminate your semiconductor in contact with an electrolyte. I show here the electrolyte. You can have competition between recombination of the holes and the electron and the reaction with the redox system in your electrolyte. For example, if you have water, if you can make a splitting of water. You can also have other redox system. So that's why it's very important to find a synthesis approach to deposit only type 1, not type 2, in order to avoid this surface state. Okay, that's what we call highly textured tungsten disulfide thin films. So I did this work with a PhD student long time ago. It's in 1995 to 1997 as well. And we use the following. It is very important to explain this kind of method, which is very innovative. What we do is the following. Sorry. Oh, I will go back. Yes. So you look here in this, I will use a pen, color. Okay. So this is, we focus on this picture here. You have a substrate. As I told you, can be glass, can be sapphire, can be any substrate. We deposit a nickel layer. You will know why. Nickel. A very small amount of nickel, very thin. Some 10 angstrom, for example. And then I deposit tungsten oxide. Okay. Then this substrate, I put in a system where I can increase the temperature. Here I can make a vacuum, or I can bring some gas, some inert gas like argon or nitrogen. That's also possible. And then I have a source of sulfur, for example. So what's happened according to this phase diagram here? If you look to this phase diagram here, there is a possibility to go from amorphous tungsten oxide, what you can deposit by evaporation, electron gun evaporation or sputtering, whatever, and by sulfurization, you have here sulfur. This is maybe I made a small mistake. That's sulfur here, and that is tungsten. So you can sulfurize the tungsten oxide, and you have a T line here, which brings you from tungsten oxide to tungsten disulfide. By a lot of sulfur, you can also have tungsten trisulfide. But don't forget we have nickel here. So if we increase the temperature to a eutectic point of nickel, the sulfur will react with nickel and form what this compound here, what I zoom here, just near the eutectic in this place here. And you have a point here where your nickel 3s2 is like a liquid, is a eutectic mixture. There is a percentage of sulfur where you have, it's around, I think, 620 degrees. You will form a liquid. This means during a certain time, you have nickel 2s3 here as a liquid in contact with tungsten oxide and a lot of partial pressure of sulfur. And what's happened, because the Gibbs energy is favorable to prepare tungsten disulfide, you will have a tungsten disulfide. And in presence of nickel, with nickel, you will have this picture, what you see here. This means this type 1 here. If you don't use sulfur, nickel, this means you have now eutectic, then we will go back to this one, to the type 2 here. Therefore, there is a possibility to prepare highly textured tungsten disulfide thin film by using this eutectic, by using an additive nickel sulfide, very, very thin, something like 5 to 10 angstrom, is a very small amount, which is just here to allow this type 1 to grow instead of type 2, which is what we don't know to have. So that's one method, which is at the time when we did this work, is very original and allowed to have a very highly textured tungsten disulfide. So students, they have worked on this, and they prepare a PEC, what we call photoelectrochemical solar cell. And I show you again and again this diagram. You see here the vacuum scale, and here the electrochemical scale. And I want you that you remember now that 0 in the electrochemical scale here is the redox couple H plus H2. And it is exactly in the level of minus 4.5 electron volt in the other scale, the scale of solid state, the solid state scale, which is related to the vacuum. So when you are making density function theory, for example, you are working with this scale here versus the vacuum. What I show here is the valence band of the tungsten disulfide. It's a p-type material. It's grow as a p-type material. Here is the conduction band. When you illuminate this material in contact with electrolyte, and they use this electrolyte here, Fe2+, Fe3+, redox system here in this place, it is exactly at around plus 0.771 volt here. And here you have the redox system of water. You have here a metal. And as you should know that when you have a metal in an electrolyte like this one, this level here is exactly the level of the redox system. And I use the most sample reference electrode, which is silver saturated silver chloride. Okay. And when you eliminate this, you have electron and holes. Holes are stay in the valence band, and the electron got to the conduction band. Of course, you should have light energy bigger or equal to the band gap. Of course, if you have a excess of electron in the conduction band and excess of holes in the valence band, then you will have, according to statistical physics, two Fermi level, one for electron, what we call quasi-Fermi level for electron, and one quasi-Fermi level for holes. Quasi-Fermi level for holes. And in between this point here and this point here is the voltage, which you can develop by illuminating. So in this part of the semiconductor until here, when the light is absorbed and the thickness is about 1 over alpha, alpha is the absorption coefficient, you have a non-equilibrium, and you have to use the statistical physics under equilibrium, but a little bit with some modification by delta N and delta P to get this quasi-Fermi level. What's happened when the electron and hole are on the valence band for holes and the electron in the conduction band? There is different things can happen. For example, if you have what I show you here, this an amount of this type 2, then you will have a lot of dangling bound. This means a lot of surface state. If you have less, then you are lucky. And if you have a good material, only type 1, then of course you will not have the competition between recombination and the reaction what you like to have. So we use iron 2+, iron 3+, because we want to make a photoelectrochemical solar cell in photovoltaic mode, what we call. That's why we have a redox system which is well defined. And the student he worked on this work, he was able to characterize his material, and I show you here again how we characterize a material. What we need a lamp. There's a lamp here. It can be a tungsten lamp, what you can buy in the easily, or a xenon lamp, which is a little bit difficult to, it's a little bit expensive. Why? What is the difference between xenon lamp and tungsten lamp? Xenon lamp have more ultraviolet. So for example, if you have large semiconductor band gap, this means the band gap is above 3 electron volt, then you need to use a xenon lamp. But if you have a band gap less than 3 electron volt, like tungsten disulfide, you can work with tungsten lamp because you have a lot of visible what you need. So either you use the tungsten lamp or xenon lamp. Good. Another thing what you have to be very careful about is the spectra. If you have here I show you a xenon lamp, what they call arc lamp. Tungsten lamp, it's a small lamp with 120 watt. And I compare it to the AM 1.5 global. AM 1.5 is the sun, is the light of the sun in the zenith. And we have discussed this many times during my course. So you see the red one here is the AM 1.5. And you see none of these two lamps are matching exactly the sun spectrum. That's why you have to measure your lamp before making your measurement, and you normalize your current when you are making the measurement. Okay. What we use to do the characterization, we use what we call a potentiostat. The potentiostat allowed to give a controlled voltage between the reference electrode and the working electrode. And the potentiostat can measure the current between the counter electrode and the working electrode. That's why you need a 3 electrode compartment, 1 reference electrode, 1 working electrode, which is your tungsten disulfide, for example, or any semiconductor what we want to study, and a counter electrode, donc 3 electrodes. And here you have in your potentiostat 3 input, 1 for the reference electrode, 1 for the counter electrode, and 1 for the reference. Why we use this box here? Because we don't want to have light, or we want to measure your solar cell in the dark and under the light. That's why we have a shutter here, which can blend the light. And then after you have your characteristic in the dark, you can make your characteristic under the light. Or you have a shutter which is turning with a kind of frequency in order to see once you see in the light and once you see in the dark. The potentiostat is working like this. It will give you a voltage proportional to the time with a given scale here in millivolt per second. And then you measure your current. And then the potentiostat, or the electronic in your potentiostat, there are some electronic which with some resistance and so on, which allowed that the current is going only between the working electrode and the counter electrode. So now current flow across the reference electrode, because the reference electrode has to stay reference where the potential is always constant. So this is the way how we do the photoelectrochemical measurement. It's very important. Okay. Here's some result, and if you like, I can send you this paper. It's from 1997, what we prepare with the student, Matthias. He's the student. He got his PhD at this time. And you see here, for example, the characteristic IV, where we use the shutter here, and the tungsten lamp. And we can make the light on and light off, like you see here, for different voltage. And you can see that we have prepared some 10 film of tungsten disulfide, which is photoactive. At the time, it's the first time we are able to make this. So we use a potentiostat, which we scan at different scan rate, and then we have this curve here, and then we can shut on and off the light, and we see this curve. And of course, this curve will show you the dark characteristic and the characteristic in the light, and in between here, this is the magnitude of the photocurrent what we got with this in this system. It's about something like milliamps per square centimeter. So this is the schematic what I showed you before, where you have the metal. This means you have your system iron 2 plus, iron 3 plus redox system here. Of course, this is very preliminary results. If you want to have more, to understand more about this current, you have to do a lot of work. And in the next time when I come back, the next Friday, maybe not next Friday, because next Friday we have another subject, but we will show you other method where you can go much deeper in this investigation to make the photoelectrochemistry of semiconductor for water splitting or for the production of a current, etc., etc. So I will stop here, and I hope the student is here now.
Yes.
So I will give him the floor. So is the student is here? Is already there?
Yes, both Prof. Abdelillah also.
Okay, very good, very good. Then I will give the floor to Abdelillah, if he's here. Okay. And he will present that.
Your mic,
So,
Prof. Abdelillah.
You open your mic? Yes.
Thank you, Ustad Salim. Thank you, Professor Ahmed. The talk today will be given by Zouhir Mansouri from the Laboratory for Condensed Matter and Interdisciplinary Science, the Faculty of Science, Mohammed V University in Rabat. He will give a talk on 2D black phosphorus nanomaterial for battery, lithium-ion battery. He prepared his PhD in Faculty of Science in Rabat on this topic, 2D materials, and the phosphorus especially. You have the floor, Zouhir, for your presentation.
Okay, hello everyone. Thank you, Professor Benyoussef, for this nice and kind introduction. I'm very pleased to be here to talk about lithium-ion battery at the virtual learning university. I would like also to thank the organizer who have given me this opportunity to share and to share my insights and ideas about lithium-ion batteries. A little bit about my background. As Professor Will said, I have a master's degree in computational physics, and now I'm pursuing a PhD at LaMCScI lab, working on developing new electrode materials. I mean, anode-based black phosphorus, under the supervision of Professor Omar Mounkachi and co-supervised by Abdelillah and Abdelillah and Abdelillah Benyoussef. And so in my today's presentation, I'm going to be talking about approaches and development instability of the black phosphorus nanomaterial toward next generation energy storage device. So as you see in the title, I'll be focusing more on black phosphorus, its advantages as a new electrode material for energy storage, especially for sodium and potassium. And of course, I'll be sharing some theoretical results that we have done by density functional theory calculation. The thing that I want also to share is that I'm not going to talk about the importance of replacing traditional energy by renewable and sustainable energy, since the previous seminar have already mentioned the problem that we are facing, especially pollution and global warming. Instead, I'll be focusing more on the topic of storing renewable energy, especially one of the most important devices is lithium-ion batteries. So I'll focus more on lithium-ion batteries. The main content of my talk will be like this. First, I'll make a short introduction on the lithium-ion battery, how they work, discussing some important parameters defining better batteries. Then I share some issues facing either lithium or lithium-ion batteries or lithium metal, and opening the door to alternatives like sodium and potassium. Then I go to talk about black phosphorus, its allotropes, advantages in energy storage. And of course, black phosphorus suffers from some issues, and one of them is instability issues. And I'll cover them. And I'll cover also some strategy that has been proposed to increase its instability. And one of them is building heterostructure. Then I finish my talk by giving some conclusion and perspective. I mean, what we are now in terms of stabilizing black phosphorus. So first of all, why, let me check for, first of all, why did lithium-ion battery is so prevalent? If you look at this plot, you will, which shows the volumetric energy density versus specific energy density, you see that both the volume and mass basis lithium-ion are way more energy dense than other chemistries like lead acid and nickel cadmium. So you see the progression along from small lead acid to nickel cadmium, nickel metal hydride, and lithium ion batteries. So now all the world are using lithium ion batteries. And these commercialized in 1991. And lithium ion batteries are so nice compared to the other chemistries. Not they do have the highest energy density, but also they have no memory effect, which means we can charge it or discharge it, and and it doesn't affect its capacity. And they have also low toxicity, especially lithium iron phosphate, which they don't contain heavy elements. They have also the longest lifetime among all of this kind of chemistry battery here. And now it is important to know how they work. And probably many of you know this before, but I want to kind of put all us on the page in terms of what happened inside the device. This is a general schematic of a lithium-ion batteries. You see it consisted by three essential elements. You have anode, cathode, and the electrolyte. I'll start from the left. Here we have a common collector, which is basically a piece of foil that conducts electricity, and it's ultimately connected to the exterior. And here we have anode, which is graphite. Now graphite and graphite is actually complex by polymer group, and sometimes people they use conductive additive like carbon to help the whole film be more conductive. On the other side, we have also a current collector, which allows electron in and out. Here we have the cathode, which is an organic material, and is also stuck to the current collector by polymer. In general, many of commercialized cathode material are layered materials or sorts of structure in which lithium can move in and out of the structure without disrupting the primary structure of the material. In between the anode and cathode, we have a piece of plastic films called the battery separator. It's a pure film. It's really serve one primary function. It's to prevent the anode and the cathode from touching each other electrically. The separator, it has to have holes in it because we need ions to move from the cathode and to the anode and vice versa. Surrounding everything is liquid electrolyte. So the liquid electrolyte has to solve the lithium ions as they come out either from the anode or the cathode. This is a general diagram during the charge or discharge. Let me point out before that the conventional lithium ion battery is produced by graphite as anode, and lithium cobalt oxide as cathode, and the electrolyte as a liquid solution of lithium salts in a mixture of organic solvents. So during the charge, for example, the lithium cobalt oxide is oxidized, as you see here, following the first equation. Then the graphite gets reduced following the second equation, and the whole system gives an output voltage around 5 volts. Then I'm showing some criteria for choosing electrode material, and the most important one is voltage, primarily governed by thermodynamics. And we have also the capacity to define as how much ion can be stored in a given mass.
Zouhir, il faut s'approcher du micro.
I said the capacity or we can see it as how many crystallographic fields available host ions, which give
Il y a toujours un problème de micro, Zouhir. Il y a un problème de micro. Il faut s'approcher du micro.
I think I have to make the earphones. Could you hear me now? Professor Benyoussef? Could you hear me now?
Sometime yes, sometime not.
Maybe it's the bad connection. Try again.
Okay, I said the energy is the capacity multiplied voltage. Could you hear me? Could you hear me?
No, we don't hear you very good.
Okay, sorry for that. What about now? Could you hear me well?
Yeah, I hear you now.
Okay, I said the power is determined as how fast energy can be extracted. So the ions and the electrons need to be extracted as quickly as possible from the material. So ionic and electronic mobility are so important. We have also the stability. we need our material to be stable. I mean, during the charge and discharge. Of course, we need our battery to work as many years as possible. In terms of cost, if we want to decrease or lower the cost, one needs to be to handle the raw materials or change the raw materials or change the synthesis process. During the lithium insertion in the host material, there are several kind of mechanisms that happen in materials, and we can classify them on three categories, either for anode or cathode. For anode, for example, we have intercalation materials like graphite and conversion material like sulfide or phosphate. And we have also alloy materials like silicon or germanium. And we have on the cathode side, we have layered material, lamellar materials like lithium cobalt oxide, and spinels one like lithium manganese oxide. And we have also polyanionic materials like olivine or lithium iron phosphate. So keep in your mind, we need to increase the voltage of cathode, and we need to a material that has lower potential in the anode to have an output, a high output voltage. But one needs to be careful with the electrolyte, because we need a cathode that has energy higher than the HOMO to avoid oxidation of the electrolyte. And the anode side, we have the energy of the anode to be lower than LUMO to avoid reduction. So in the following, I'm not going to talk more about electrolytes or solvent that has been used in the electrolytes or either for cathode. I'll focus more on the anode side. As I said before, graphite is the most commonly used anode material for lithium-ion battery, and it has a capacity of 370 million per gram, which seems to be insufficient. On the other hand, lithium also suffer from some, lithium elements suffer some issues. Its distribution on the Earth is very limited, which means the cost will be high regarding the new market that require more energy. So alternatives are very demanded, and research are made huge efforts in this regard. And what I found in the literature that there are 4 kinds of batteries that has been attracting research attention, like high energy density batteries like magnesium ion, or safety batteries like solid state lithium, or specific energy batteries like lithium air or lithium sulfur. And we have also low cost batteries like lithium ion or sodium ion. And I focused in my thesis on this kind of batteries, sodium ion. Not only they have low cost or widely available, but also they have similar chemistry to that of lithium. Now the challenge for this, for potassium and sodium, is to find host anodes. Unfortunately, the commercial anode is graphite, and it's not suitable for to host sodium or potassium due to its smaller interlayer distance, which regarding the big size of sodium, which gives a lower capacity, like for sodium, we have capacity around 35 million per gram, or for potassium, we have 279 million per gram. In addition, the traditional anodes, they also suffer. They cannot be used for sodium or potassium because they have limited capacity and swelling problems. Regarding this, an article published in 2015, where they proposed to use black phosphorus for, as anode material, where they studied the mechanism of sodiation. They found that the system proceed into 2 steps. The first one is intercalation, where the sodium occupy the seat exists in between layers until the whole seats are occupied. Then the system start the second step, which is alloying, until forming a new phase, as you can see here. where each phosphorus atom is surrounded by 3 sodium, which gives a high capacity as high as 96 milliampere per gram, which is about 7 times that of graphite. But what happens when they cycle this capacity? You can see this which is a problem here. And they revealed in their paper that the problems come from the volume changes during the charge. Here, during the charge, a huge volume about 500% has been observed, which means that the black phosphorus, when it charged and discharged, they cannot return to its primary structure. So there is a challenge here, is we need this capacity, we need our material to maintain its capacity as high as possible and as long as possible also, and we need to increase its conductivity and also increase its stability. And since this problem mentioned for the first time, there are a huge effort toward stabilizing this capacity. And what I found in the literature, all the people, they have similar goals, is to stabilize this capacity by adopting some strategies, like I mentioned here, reduction the 3-dimensional black phosphorus into 2-dimensional structure, while adopting constructive or innovative stabilization strategies can improve the electrochemical properties of the battery. So as I mentioned here, we have 2-dimensional structure. I'll talk a little bit now about the importance of 2D materials. You know, graphene was synthesized in 2004 by Game and Novoselov, and it's showed some interesting properties. Then a huge effort have made to discover other lamellar or 2D materials. And the important thing with 2D material is they can give us a range of properties. For example, electronic properties. We have the material that show metallicity and semi-metallic and semiconducting and insulating. And also they have, according to their thickness, they have a high surface area to absorb ions. And one of the emerging 2D material and considered as a star and competitor to graphene was phosphorine. And now I'll talk a little bit about what makes phosphorine so important than other 2D materials. Before I do that, I have to mention where phosphorines come from. Here is the family tree of black phosphorus allotropes. The whole thing started in 1669, where white phosphorus was discovered. Then by playing or changing the temperature or pressure, you can get the black phosphorus or red phosphorus. And in 1914, black phosphorus was produced from red phosphorus by ball milling, and other techniques are proposed to achieve black phosphorus. And similar to how graphene was obtained from graphite, black phosphorus also can be exfoliated in one layer, and it's called black phosphorine. And here is the structure of black phosphorine. And it was discovered for the first time in 2014. And now I'll talk a little bit what is the importance of black phosphorine. Black phosphorine has interesting properties. The first one is its band gap tunability. I mean, we can tune its band gap by just, as you can see here, by varying the number of layers, or as I summarize, this plot summarized, by changing the number of layers, as I said, or by adopting some heterostructure, or by just doping by other elements, or by surface functionalization like nanoribbons. So phosphorine, with these important properties, which is ranged between that of metal dechalcogenized like molybdenum disulfide or graphene with semi-metal. So this property is so attractive for many applications. The other one is the airplane anisotropy, which is, as you can see here, phosphorine has two kinds of directions, the armature one and zigzag, which means we can control the properties along the zigzag and armchair. As you see here, the electron conductivity can be manipulated in direction zigzag and armchair. The similar way for Young modulus and other properties. The similar also for battery application. The ion can be controlled even in the zigzag or armchair direction. So these properties are making phosphorine attractive, as I said, for many applications, and one of them is energy storage. But before phosphorine gets implemented in device, one needs to handle its problem. Of course, phosphorine has also its own problem, as I'll show here. The first one is the absence of reliable techniques that can produce high quality and large area of phosphorine. Even research, they try to produce phosphorine, like they use mechanical exfoliation. They found the samples, they show high quality, but they suffer from scalability. But we have also liquid phase exfoliation, is the shape and scalable, but the material shows some low properties. The same here for the technique can be scalable, but the samples show we need to produce high quality phosphorine with high properties. So it's very demanded for application. There is another problem with phosphorine is its instability issues, which means it's very when it's manipulated under environment condition, it degrades very quickly. As you see here in optical microscopy images of fuel black phosphorus flake acquired at different exposure time under environmental conditions, you see the formation of air, oxygen or water bubbles on the surface. And here the plot shows the height of phosphorine that change over time. So phosphorine is unstable and degrades very rapidly in the presence of environmental impurities. So this has motivated a large of research to understand where is the problem come from. Here I'm showing the valence states of black phosphorus, in which phosphorus has 5 electrons at the external orbitals. Three electrons are participate to covalence with surrounding atoms, and there is 2 non-bonding lone pair electron here that makes phosphorine sensitive to air contamination. And what I found also that there is a 3 steps of degradation mechanism of black phosphorus was theoretically proposed, including the formation of superoxide under light, followed by dissociation of the superoxide species, and finally the dissociation reaction under the presence of water. But people, they also reported that not only oxygen and water can produce or can degrade phosphorine, but also there are some other parameters that accelerate degradation, like light, temperature, and band gap energy. So we see here the problem come from the lone pair electron. So coupling lone pair electron with other functional groups can help achieve the stability, and this is what other people do. To reduce the problem of phosphorine, there are several strategies that has been proposed in literature, and they classify them into 2 technologies. The first one is, we can call it surface passivation layer, in which no chemical reaction are involved, like using encapsulation with graphene and carbon nitrates, molybdenum disulfide, aluminum oxides, ionic liquids or organic monolayers, and etc. On the other hand, we have chemical reaction that's occur in I call them surface chemical modification, like using carbon sources, like graphene, graphites, graphene oxide, aryl diazonium chemistry, etc. We have also in the involvement of POC bonds like using with graphene and reduced graphene oxide, and using other elements like fluorine and azote and copper and silver and others. So this technology are used with the same goal, is to stabilize phosphorine against air contamination. And some of them, they can also help the problem with black phosphorus, which is the volume expansion, as I mentioned here. Here they involve PC bonding in the lateral, and here they involve also the POC bonds. So the strategy are used to reduce the problem with black phosphorus, and they proposed as anode materials. And in my calculation, I adopted this strategy here, which is using the encapsulation strategy, in which we put two phosphorine layers in between two layers of graphene, and then we study its possibility to be used as anode for potassium and sodium. For that, we start by calculating the capacity. Before achieving the capacity, we first started to study where the ion can be absorbed with high energy. As you see here, we have three regions in between phosphorine layer, in between two phosphorine layer, or between graphene and phosphorine, and outside graphene. And we found that the ion absorbed strongly in between the phosphorine layers. And we start by adding a number of ions until the capacity has been achieved. And we use this formula to calculate it, and we find that the capacity of the system is 533 milliampere per gram for potassium and 580 milliampere per gram for sodium. And here the system, after doing INT simulation, I mean molecular dynamic simulation at room temperature. Now I'll back to our to the black phosphorus allotrope. I missed one phase here, which is blue phosphorine, was predicted theoretically in 2014 and experimentally synthesized in 2016. Here is the structure of blue phosphorine from top view and side view. And here we have the black phosphorine from top and side view. And we want to get blue phosphorine from black phosphorus, we can just make a dislocation of the structure. And the distance between blue phosphorine layers is slightly greater than that of black phosphorus, which is 5.63. Blue phosphorine has a semiconductor band gap with an indirect band gap around 2 electron volt, and also can be tuned by external factors like varying the number of layers or applying like strain. Here you can see the band gap, the variation of band gap as a function of strain. As I said, blue phosphorine was synthesized experimentally in 2016 by just choosing by pentaxial growth, by choosing an appropriate substrate. Here, they use gold substrate 111, and then they try to find another appropriate substrate, like using gallium, nitrogen, or sulfur or copper, or by changing the techniques, the technique like using silicon intercalation or lithium intercalation here, as you see. And the same, all of these techniques, they have the similar goals, which is achieving blue phosphorine with shape method. And we need also the samples to be high, to have high quality, and to have also great properties. And blue phosphorine has been used as anode material for potassium and sodium with high capacity around 865 milliampere per gram, which is exceed of existing 2D materials. But before blue phosphorus used as anode, one needs to handle this problem. There, as you see, we need to produce high area synthesis method for crystalline blue phosphorus is needed, and we need also to handle the air instability issue, and of course we need to increase its conductivity because it has a large band gap, and structural instability during charge and discharge. And there are several techniques or strategies that propose to increase it to handle or to deal with this, blue phosphorus problem is adopting, for example, surface modification, or by just coping with heteroatom or molecules, or adopting electronic structure modulation, or by just designing new van der Waals heterostructure. And they found this one its importance, where they use several couple layers like boron nitride and hexagonal boron nitrides, or graphene, or vanadium disulfide. And in my work, we proposed BC2N, and now we will see why BC2N and what is the importance with BC2N. Boron carbonitride, it has and exhibit electronic properties between graphene and hexagonal boron nitrides, and also possess strength comparable to that of graphene. And they have also strong bonding in the layer and lack of porosity. And they have 3 isomers of BC2N. So by using BC2N, we can increase the bending energy according to the existence of nitrogen and boron in the system, as we will see in the following slide. To do that, we have started by optimizing the models. As you see here, we have 3 models here, and we choose the stable one, and we construct our heterostructure, as you see here, and the formation energy indicate that the system is stable and with until layer distance around 3.43 Armstrong. Then we calculate the best structure for the whole system. As you see here, we can reduce by introducing BC2B, we can reduce the band gap of 10 almost disappear. It became 0.03 electron volt. Then also we start to study how much ion can be stored in this heterostructure. And we start by putting atom in different region of the heterostructure. And we find also that after absorbing sodium atoms, there is a new state appear at the Fermi level, indicating the electrical conductivity are enhanced. Also, we looked at how the ion can diffuse on different regions of our system, especially in between layers. We find that it's 0.11 electron volt. It's similar to other heterostructure in the literature. And then we study the behavior of voltage of our system. We start by putting a number of ions in the most stable states until the system reached the final state, which is the voltage became negative, which means no more ion can be added, and that gives a final capacity about 763.17 milliampere per gram with a voltage around 0.25 volts. And we did also the dynamic molecular simulation that confirmed the stability of our system. So to finish my talk, what I've talked until now is blue phosphorus has interesting properties, especially for battery application, but its translation into real devices require development of reliable and low-cost techniques. And I showed also that black phosphorus has an outstanding capacity, but it's suffering from huge volume changes, which means we will have a problem with cycle life of the battery. Then I showed also that black phosphorus holds some interesting properties and may solve the problem. But if we deal with its instability, current instability issues, as well as developing cost-effective scientific method, and what I found from the that cultivation technology and nanostructuration design are a good choice to stabilize either black phosphorus or blue phosphorine or the black phosphorus. Before I finish my talk, also I would like to acknowledge the people that's helped me a lot in my thesis and helped me to achieve this work. Supervisor at Science Lab, Omar Mounkachi, and Benyoussef. Zouhir al-Fatmi at YAPI Institute, and Selma al-Hababi at MSDA, and Khadija al-Muallim from Master Foundation. So I hope my talk was clear, and if you have questions, please. Thank you.
Thank you very much, Zouhir Mansouri, for this nice talk. Before I open the floor for question and comment, I ask Professor Ahmed Ennaoui for a comment.
Thank you very much. First to the PhD student, he gave a lot of information and about the phosphorus, from black phosphorus to different kind of new founding. There are many questions what we can ask. Maybe some of them we will put it in the WhatsApp, not here. But there are some remarks what I would like to address. One is it will be very good if in the future for every talk we have different paragraph. One is to keep in mind that there are some people, they don't know about the subject. They don't know, for example, about the phosphorus, so they have to know a little bit very simple stuff regarding the subject, and there that they can at least take away something from the talk. It's not the talk is not addressed only to people they already know a lot. Of course, most of the students we have here are PhD students working on the topic, I guess. But it will be good if we have something very simple in the beginning and then make it more complicated. Another remark is we would like to know, and that's one of my questions here, the status now of black phosphorus in terms of industrial utilization, like, for example, scaling up the black phosphorus, which application actually is coming out, and that the industry is interested and they start to work on it, or if not, then we have to know that the subject is still in the basic, in the lab scale. It's very important. The other thing is we all know that if we take the black phosphorus, the 2D materials in general, we can split it in small pieces, in layered material. This is a problem for the battery, because the battery mean that your material will be electrode, anode or cathode, whatever, and then it will absorb the material. Is there any limit for this material in order to be for one application but not for the other? Like, for example, now for the storage, did black phosphorus or phosphorus in general is a good material for storage, yes or not? And if yes, why it's a good material? If it's now, or maybe it can be, but we have to do this or that. This is very, very important for application. So I would like if the speaker can give us some issue regarding the application for any application. For example, for batteries, if it's really the material which has to be definitively used for battery now, or still to explore if it's a good material or not. Thank you very much.
You have, Zouhir, you have the floor for the answer.
So for the first question is the method that can produce black phosphorus. I have to mention that one of Omar's group can produce black phosphorus with which they use typical vapor transport to produce.
We don't hear you. Can you find out why we cannot hear you very good? Is the Wi-Fi, or you have to go a little bit to the microphone?
Actually, I don't know why.
Okay.
What about now?
Now it's okay. Now it's
okay.
Good.
Okay. I said that for the first question, one of
There is a problem now.
Maybe connection problem.
Yeah, I think so. Yeah.
What about now? Can you hear it? Could you hear me?
Yeah.
Now yes.
When you start, it's fine.
Okay, I said that in the lab we can produce black phosphorus from by using chemical vapor technique, but the quality and quality is good, but the quantity is very low.
So we don't hear you very good. Don't hear you very good.
Maybe for the first question concerning the application of black phosphorus, there is a first challenge is the scale up, because it's still expensive, the fabrication of black phosphorus, still now. And the second challenge is the stability. There are many ways to make black phosphorus stable for 2D material, for phosphorus. There is a challenge to make it more stable by passivation or to some functionalization of the surface. But at my knowledge, it's not for the in the industrial level, not yet.
Yeah, okay. Just because it's very good to discuss this issue. If you take, for example, silicon. Silicon is a material which is not stable. But as a matter of fact, that you can saturate, saturating the dangling band in the surface with silicon oxide, for example. Then it's stable and there is no problem. And of course, one has to use different method in order. If you want to make a device, you cannot just make it in air. So if people a long time ago in Bell Telephone, for example, in 1950, they just say, okay, silicon is not stable, then we just leave it. Then we will not be now in this situation with smartphone, with all this technology. But they find out how to make it stable, how to work in condition like white rooms, green rooms, etc. And they make device, and you see what is the situation now with integrated circuit and VLS technology, etc. So, of course, it's the problem of phosphorus is the same. There is, I guess, oxidation.
It is the same, and the research is in the same way by making some heterostructure encapsulation to make it more stable.
Yeah,
and,
yeah, exactly. Yeah,
it's the same way.
Yeah, yeah.
And the second question concerning two small pieces for 2D materials. Of course, the production of 2D materials by solvent exfoliation gives some small pieces of 2D material. And this is also a challenge to make a big 2D materials, at least micrometer 2D materials.
Yeah, yeah.
With only a tick of 1 atoms or 2.
Yeah, yeah.
Okay, the floor is open for question and comment from audience. Are there some question for Zouhir, Mansouri? Another question by Professor Ahmed Ennaoui is for storage. It has been shown also that black phosphorus is a good material for hydrogen storage. A good material with the desorption temperature around the room temperature and a high capacity, gravimetry. It's good for hydrogen storage also.
Yeah, yeah, yeah.
Other question? And use the chat for your question.
So there is now question in the chat. Maybe I just want to say to people that next week, this means the 14th of April, there will be 2 talks. Each one is 30 minutes. So one is from Leo from Italy, and one from LaMCScI, and all about the soiling of PV. As you know, the PV panel, when you buy a PV panel, and we told you it's or you buy a project, a big project like NOR 1, NOR 2, which is not PV, but it's CSP, or now if Morocco buy 1 gigawatt PV system, 1 gigawatt mean that the panel is clean, there is no dust, and it's working at its maximum. This means the sun is 1,000 watt per square meter, and so on. But if there is some dirt after some days exposing the PV in the field, it will decrease. And this problematic of soiling is a big issue. Million or billion will go if we have by 2050 in Morocco more than 53% of renewable energy in Morocco. Therefore, the subject will be very good to work on, and we have a good scientist working on this field since long time, LaMCScI and Leo, and they will talk about it next week. I mean, by 14th of April 2023. So just that you know this. you can look in the chat. We don't hear you.
Il y a une question sur le chat par Hassan Mounir. Est-ce qu'on peut utiliser le matériel 2D comme électrode pour catalyseur? Zouhir, vous avez une réponse à cette question? Mansouri. Alors, pour répondre à cette question, en fait, matériaux 2D ou matériaux avec quelques couches de matériaux 2D peuvent être utilisés à condition que le matériau lui-même soit un catalyseur. Hein. Il faut qu'il y ait, comme le professeur Ahmed Ennaoui l'a expliqué à plusieurs reprises, on peut utiliser le matériau avec des caractéristiques, semi-conducteurs, etc. Mais il faut que ce matériau possède les potentialités de catalyseur pour être utilisé comme catalyseur. Et pour les matériaux 2D, il n'y a pas d'objection à ce que ça soit utilisé comme catalyseur. Bien sûr, reste la question de la mise en forme pour l'électrode. Si vous avez un commentaire, professeur Ennaoui.
Oui, oui, je peux ajouter autre chose. Il y a des qu'on appelle baseline, c'est-à-dire des propriétés qui sont faciles à comprendre. Il suffit de regarder l'échelle électrochimique, par exemple, regarder où se trouve le couple redox de l'hydrogène et de l'oxydation de l'eau, c'est-à-dire H plus H2 et H2O2, et entre les deux, il y a 1,23 thermodynamiquement 1,23 électronvolts. Où se trouve? Qui dit où se trouve, ça veut dire il faut savoir quel pH vous travaillez. Est-ce que vous travaillez dans le pH basique? Est-ce que vous travaillez dans le pH acide? Et où exactement? En tout cas, il y a 0,26 millivolts par unité de pH. Disons, ces deux niveaux, ils se déplacent avec 0,26 millivolts par unité de pH. Donc, ça, c'est la première des choses. Donc, une fois que vous avez le pH, vous savez où se trouve ce couple redox, disons, séparé de l'eau. Ça, c'est le premier. Où se trouve votre semi-conducteur? La bande de valence, où se trouve la bande de valence de votre semi-conducteur. Le DFT peut vous donner disons, une prédiction. La bande de conduction, c'est votre bande de valence plus le gap. Et vous avez votre bande de conduction. Donc, vous pouvez déjà situer votre semi-conducteur par rapport au couple redox. Si vous voulez savoir expérimentalement où se trouve votre semi-conducteur, bande de valence, bande de conduction, au flat band potentiel, c'est-à-dire quand les bandes sont plates, il faut faire des mesures de capacité, par exemple. Et ça, j'en ai déjà parlé. Je vais, la prochaine fois, si le temps nous le permet, je vais le détailler pour que les étudiants sachent expérimentalement comment on mesure, disons, comment on situe expérimentalement la bande de valence et la bande de conduction. Donc, votre système redox doit être entre la bande de valence et la bande de conduction. Mais ça, c'est seulement pour dire que thermodynamiquement, vous pouvez faire la production d'hydrogène ou une autre réaction quelconque que vous connaissez. Maintenant, la thermodynamique ne suffit pas. Si thermodynamiquement, vous pouvez faire la production d'hydrogène ou la décomposition de l'eau, cinétiquement, ça veut dire combien? Si vous allez sortir 3 bulles tous les heures, 3 bulles d'hydrogène tous les jours, ça, ce n'est pas intéressant du tout. Vous voulez beaucoup d'hydrogène. Hein? C'est un problème. Donc, il fallait étudier le problème cinétiquement. Cinétiquement, ça veut dire votre matériau doit avoir ce qu'on appelle, grosso modo, catalytique. Il est catalytique, c'est-à-dire combien de litres d'hydrogène il va produire pendant un delta T donné. Et ça va dépendre comment la nature de votre bande de valence. Si vous prenez le silicium, par exemple, le silicium, il a une bande de valence SP, hybridation SP. Mais si vous éclairez le silicium, vous aurez beaucoup de trous pour le type N dans la bande de valence ou beaucoup d'électrons pour le type P. Mais ces trous, ils sont là, ils peuvent aussi bien faire la décomposition de l'eau, c'est-à-dire oxyder l'eau, mais ils peuvent aussi oxyder le semi-conducteur lui-même. C'est-à-dire c'est comme un serpent qui mange sa queue. Donc, il faut éviter que les trous oxydent le silicium. Et ça, c'est un problème. C'est pour ça que le silicium n'est pas un bon candidat tel qu'elle est pour la décomposition. Donc, il fallait que les trous dans la bande de valence oxydent l'eau, mais pas le semi-conducteur. Et là, il y a, si vous prenez les matériaux de D, déjà, ils sont très stables parce que la bande de valence, elle est composée de la bande D, de l'orbital D. Parce que vous avez un élément de transition, le WS2 par exemple, ou bien MOS2, ce sont tous des éléments qui ont ce sont des éléments D du tableau de Mendeleïev. Donc, vous trouvez le caractère D dans la bande de valence, EG, ça s'appelle, et dans la bande de conduction. Donc, le trou qui se trouve dans la bande de valence, à côté d'une liaison, il est, comme la liaison il est dans la bande de valence et dans la bande de conduction, il est encore lié à sa liaison. Donc, il ne va pas y avoir une oxydation du matériau. Donc, si on compare une bande de valence qui a le caractère D, une bande de valence qui n'a pas le caractère D, c'est-à-dire SP, etc., eh bien, ces matériaux de D, ils sont plus stables de ce point de vue. Ou tout matériau, même un matériau 3D qui a la bande de valence qui a le caractère D, il est très stable. Donc, déjà, cette stabilité du matériau, il est là. Maintenant, est-ce que cette stabilité est suffisante? Il fallait voir comment se fait le mécanisme pour la décomposition de l'eau. Quelles sont les étapes? Plus dans la catalyse, les étapes sont petites, il n'y en a qu'une ou deux étapes pour décomposer l'eau, plus c'est intéressant. Et ça, c'est une question de recherche. Il y a beaucoup de matériaux maintenant qui ont montré qu'ils sont de bons matériaux pour la décomposition de l'eau. MOS2, c'est un bon matériau. WS2, c'est un bon matériau, etc. Mais ils ne sont pas très, très performants. C'est-à-dire il y a encore des petits problèmes. Donc, à mon avis, il fallait qu'on continue à discuter ce problème de catalyste chaque fois et qu'on ramasse le savoir petit à petit. Mais sachez qu'il n'y a pas encore un matériau, un semi-conducteur qui est extrêmement performants. Mais il y a, si vous prenez les matériaux avec un gap très grand, les perovskites avec le gap très grand, comme si vous prenez TO2, si vous prenez les matériaux BaBO3, ils sont tous des matériaux qui sont, lorsqu'on les met sur la surface, RuO2, O3, si on les met à la surface d'un semi-conducteur performant, au point de vue, disons, production de trous et d'électrons, eh bien, c'est des couches très minces de TO2, des couches très minces. Quand je dis mince, c'est vraiment très, très mince. Il ne faut pas que ça contribue avec une résistance. Il faut que ce soit extrêmement mince, que l'électron passe directement par effet tunnel vers l'électrolyte. Hein. Là, on a des systèmes qui fonctionnent bien. Donc, les matériaux de D viennent déjà avec des propriétés qui sont favorables, à savoir leur stabilité, mis à part le phosphorène, je crois, qui sont encore que vous êtes en train d'étudier, parce que moi, je ne connais pas beaucoup de papiers qui ont fait de la photoélectrochimie avec le phosphorène, par exemple. Pour dire quelque chose, par contre, avec WS2, WSE2, MOS2, MOSE2, il y a plein. Et ils sont assez stables pour la production d'hydrogène et de l'oxygène, la décomposition de l'eau en général. Donc, il fallait qu'on continue à discuter ce problème-là pour que les gens qui font la DFT, quand ils introduisent un métal ou des atomes du tableau de Mendeleïev, qu'ils choisissent en connaissance de cause. En connaissance de cause. Et vérifier expérimentalement après. Donc, voilà grosso modo. Donc, il y a le thermodynamique, l'aspect thermodynamique, l'aspect cinétique et le mécanisme de production, de décomposition de l'eau. Quelles sont les étapes? Les étapes pour la décomposition de l'eau, ils sont faciles.
Merci, professeur Ennaoui. Donc, il y a une autre question dans le chat. Y a-t-il un cas où on a trouvé une ressemblance dans les caractéristiques pour les trois formes, couche mince, nanoparticules et état massif, pour un matériau donné? Voilà, c'est ça la question. Est-ce que pour un matériau donné, il y a des cas où les caractéristiques ne changent pas en fonction de la dimension? La réponse générale, c'est différent, hein, parce qu'en changeant la dimension, on change la structure électronique. Si le matériau est semi-conducteur, le gap augmente lorsque la dimension diminue, et donc les propriétés électroniques qui dominent toutes les autres propriétés, et la majorité des autres propriétés, que ce soit optiques ou électriques, etc., ou magnétiques, vont changer en changeant la dimension. Donc, en général, les propriétés changent avec la dimension.
Oui.
Est-ce qu'il y a d'autres questions? Donc, s'il n'y a pas d'autres questions, je remercie le speaker, Zouhir Mansouri. Je le remercie pour sa présentation, cette très belle présentation, pour l'effort fourni. J'invite les autres étudiants à se proposer aussi pour présenter leurs travaux de recherche, même s'ils sont tout à fait au début. C'est une bonne chose d'avoir des remarques pertinentes pour orienter dans la recherche. Et donc, je vous invite à proposer des abstracts pour cette série de séminaires. Donc, vous pouvez proposer votre séminaire et envoyer un abstract. Et je remercie le professeur Ahmed Ennaoui pour cette série de conférences de cette université virtuelle de l'enseignement et remercie Ustad Salem pour la plateforme Zoom qui est toujours ouverte pour les orateurs, mais aussi pour l'audience. Merci à vous tous et on se donne rendez-vous la semaine prochaine avec 2 conférences, comme a dit professeur Ennaoui, sur cette thématique très pertinente, soiling, qui empêche les panneaux solaires de fonctionner correctement lorsque les conditions ne sont pas favorables. Donc, merci à vous tous et à vendredi prochain, toujours à la même heure, 4h30, heure du Maroc.
Exact. Ouais.
Merci à vous et au revoir.
OK. Au revoir.
Au revoir.